Okay, welcome back to part 2, 11.4. So here's going to be our new test that we're going to look at. It's called the limit comparison test. It now states that suppose again you have your two sequence function series here. They're both with positive terms just like before. But if you take that series that you made the comparison with, and now we divide it into the original sequence function, we take the limit as n approaches infinity, and if this equals a constant finite number, and that constant number is greater than 0, then either both series converge or both diverge. So when you find that similar series, and if it says it converges, and we do the limit comparison test, and we get a positive value greater than 0, and it's finite, then they both converge. Or if your series that you compared it with diverges, and we do the limit test, and we get a c value greater than 0 and finite, then they both diverge. So here was our previous example. So let's jump ahead to this. So again, this will be abbreviated LCT. So this was our similar series that we had for comparison. So we know it diverges. So this is my original a sub n. This will be the b sub n. So now we're going to take a sub n divided by b sub n. And we're going to take this limit as n approaches infinity. Well, this is going to be an ugly fraction. And can we all agree that when you divide by fractions, we end up multiplying by its reciprocal? All right, so if you want to shortcut this first step, instead of writing the division and go ahead and multiply by its reciprocal right away, that's perfectly acceptable. All right, so we're going to do some canceling here. Like we said, the 12s can cancel out. We're going to have the limit as n approaches infinity of now n times n squared on the top over n squared plus 4. Well, this is like doing your horizontal asymptote. This is case number 2. Top powers equal to bottom power. So 1 over 1, the leading coefficient ratio of 1 over 1, that's my limit. Well, 1 is a finite number. It's positive and greater than 0. So therefore, we now proved that this original series is going to diverge, but now it's by the LCT. Okay? So if you do a comparison test and you do it like we were doing the first 4 examples and it fails, then just jump over to the limit comparison test right away and get it done. All right, next example. Okay, converge or diverge. Again, step 1, find the similar series. Well, we're going to get rid of the 5. We're going to cancel an n with an n down here, so 3 over 2n squared. And again, you can see that this is a p series, n to a power. 2 is greater than 1, so this converges. So step 2, if we use the limit comparison test, all right, take the original sequence divided by our comparison sequence. And again, like we said, if you don't want to show the division, just go ahead and multiply by the reciprocal right away, because that's what we're going to do anyhow. The 3's are going to cancel. We'll have n cubed over, we'll have 2n cubed over 2n cubed plus 5. But again, same power on the top with the power on the bottom. Leading coefficient ratio 2 over 2 is 1. That's going to be your limit. And again, 1 is greater than 0 and 1 is finite. So since our comparison series converges, therefore our original series also has to converge. All right. Oh, again, by the LCT test. I'm going to have to get a new mouse. This is way too sensitive. All right, example 7. Okay, find me the comparison series. Pause the video and play again to double check we got the same thing. Okay, welcome back. You should have gotten 17 over 5n for the sequence function. Drop the minus 7, simplify the ends, and this is what we're going to compare it to. All right, so now we're going to use the LCT test. Look at this comparison series. It's n to the first power which tells me it's going to diverge for that harmonic series. So original sequence function divided by our comparison function, multiply right away by its reciprocal, and let's do some cleanup here. 17 cancels 17. I'll have 5n to the fourth over 5n to the fourth minus 7. Again, I'm noticing a pattern here. Same powers top and bottom. 5 over 5 is equal to 1. That's greater than 0, and it's finite. So therefore, my original series is also going to diverge by the LCT test. Okay, so again, this is a great test to do if your direct comparison test doesn't work. You've got all the information here, just jump over to the LCT test right away. All right, example number 8. Converge or diverge. Find your similar comparison. So pause, find me that series. Okay, welcome back. Here we go. I'm going to drop the 1s. So that's 2 to the n over 5 to the n, which is going to make this a geometric. That's going to be 2/5 to the n power. So r is 2/5. It's less than 1. It converges. So notice now when I use the LCT test, I went right away to multiplying by its reciprocal. Ooh, this is going to be interesting. Okay, so here we want to work smarter, not harder. If we want to take the limit as n approaches infinity, what we really want to have with our fractions is we really want to have the 5 to the n in the numerator over this 5 to the n plus 1, and the same thing here. So what I'm going to do is I'm going to swap out. This is absolutely true. If I multiply these two bottoms, it doesn't matter which order I multiply the denominators in. So I match the 2 to the n power over here. So that way I have the same bases to that n power. And the same thing over here. Get those base 5s to match up. Now, this is one of our identities for limits that says you can find the limit of each one of these separately and find out what their limits are and multiply them together. Well, this is going to be approaching 1. The top is going to be just 1 unit bigger than the bottom, so we're always going to be approaching 1. And the same thing over here. The denominator will be just 1 bigger than the top, so we're getting closer and closer to 1 every time. So 1 times 1, that's equal to 1. That's greater than 0, and 1's a finite number. So therefore, the original series also has to converge by the LCT test. Okay. Again, it is important to keep in mind the distinction between sequence and a series. A sequence is a list of numbers, whereas a series is the sum. With every series, so whenever you see the summation, say series, there are associated 2 sequences. The sequence a sub n of the terms and the sequence s sub n of the partial sums. So keep that in mind. All right, example number 9. Whoa. This one's going to be a little difficult. So let's see. Converge or diverge. A similar series is, I think I'm just going to look at what's on the inside of my tangent function. Just the 1 over n. Okay, so that's going to be a harmonics or p series. 1 is less than or equal to 1, so this diverges. Okay, so my limit comparison test will put the original tangent of 1 over n in the numerator, 1 over n on the bottom. The problem here is 1 over infinity is going to be approaching 0. The tangent of 0 is 0. 1 over infinity, like we said, is 0. So we have 0 over 0, which is an indeterminate form. So we're going to have to take L'Hopital's rule into play here. So I'm going to change it from sequence notation to function notation, because that's when you can use L'Hopital's rule. So taking the derivative of tangent is secant squared of 1 over x, and then multiplied by the derivative of 1 over x, That's going to be negative 1 over x squared. Remember, 1 over x is x to the negative 1 power. So when you take the derivative, we bring down the negative 1 to the front and subtract 1 from your power. So that makes it negative 2, which puts x squared in the denominator. Well, 1 over x is going to be the same derivative as this 1 over x. So we'll put, wait a minute. I just noticed if I've got these two top and bottom here, they're going to cancel out. So now we're looking at the limit of secant squared of 1 over x as x approaches infinity. So again, 1 over infinity is 0. All right, so let's see. Secant is the same as 1 over cosine. So cosine of 0 is a 1. So 1 over 1 is 1, and 1 squared is 1. So therefore, our original series has to do the same thing as what our similar series has to do. So our original series will also diverge, and we prove that by the limit comparison test. Okay, example 10. Does this series with the sequence function 5 plus 2n over 1 plus n squared squared converge or diverge? Yeesh. All right. Dang mouse. All right, so our similar series. Let's see. What's going to be important here are these n's. These constants mean nothing. Get rid of them. So I see 2n over n to the fourth, or I can cancel one n top and bottom, 2 over n cubed. All right, so again, this is going to be a p series. 3 is greater than 1, so this converges. All right, so let's go use our limit comparison test. Let's take the original and divide it by our new series, our comparison series, or multiply by its reciprocal right away, n cubed over 2. Okay, so if we multiply this out, we're going to get 2n to the fourth plus 5n cubed. All right, so down here, if I multiplied out 1 plus n squared, or n squared plus 1, that would give me n to the fourth plus 2n squared plus 1. Multiply everybody by 2, you get 2n to the fourth plus 4n squared plus 2. But again, these terms on the back here don't matter because you're looking at those leading terms, and it's just like using your horizontal asymptote rule. Same power on your leading terms, then your limit is your leading coefficient ratio, which is 2 over 2, which is 1, which is greater than 0. It's finite, and therefore our original series has to do the same thing as our series that we're comparing it to. So therefore, the original series converges by the LCT test. Okay, number 11. Converge or diverge? Okay, so let's go ahead and find a similar series for this comparison. We probably want to get rid of the plus 1, which isn't going to do us any good. So that leaves me n squared on the inside. Taking the square root of n squared is n, times the n on the outside is n squared. So we're going to compare this to 1 over n squared, which by p series, 2 is greater than 1, which tells us this converges. All right, so time for our limit comparison test. Okay, well, take the original sequence. I'm going to multiply by its reciprocal, n squared over 1. We're going to take the limit as n approaches infinity. So we're going to get n squared. Oh, wait, this n can cancel with this n up here, so that's n over the square root of n squared plus 1. Well, how do we take the limit of this? Because n squared is inside the square root. This is where you divide every term by the biggest term on the bottom. So we're going to divide technically everything by the square root of n squared. So on the inside, n squared over n squared plus 1 over n squared. On the top, n over the square root of n squared is technically just an n. So we'll cancel and reduce. We're going to get 1, 1, and we have this 1 over n squared left. Well, now as n approaches infinity, 1 over infinity squared, this is going to approach 0. So that's a 0. So the square root of 1 is 1. So 1 divided by 1 is 1. Again, that's a finite number greater than 0. So our original series has to do the same thing as our comparison series. So that converges also by the LCT. All right, example 12. Holy cow, this is getting uglier and uglier. So here, let's find our similar series. And I guess we're going to do the direct comparison test and the limit comparison test and show you that they both work. So n minus 1 over n squared, well, let's see. N square root of n is like n to the 1/2 power. So that's going to be n to the 5/2. Get rid of the minus 1. So one of these n's can cancel with one of those n's. So instead of 5/2, we'll call it 3/2 on the bottom. Okay, and 3/2 is greater than 1 for your p series, so this is going to converge. So if you use your direct comparison test, n minus 1 over n to the 5/2, that's this original sequence function, just simplified that bottom denominator, less than or equal to 1 over n to the 3/2. We cross multiply. Okay, multiplying both sides by 5 over n to the 5/2 power cancels this out. Over here, this is going to give me n to the 5/2 over n to the 3/2, which I will subtract powers, which gives me 2 over 2 or 1. The n's cancel, so negative 1 is less than or equal to 0, which is a true statement, and therefore my original series converges by the direct comparison test. Whereas if you wanted to do the limit comparison test, which is also perfectly legal to do, instead of dividing by this fraction, multiply by its reciprocal. So here again, if we did a little work, we're going to have to, probably should have used n to the 5/2 here, so this would simplify out to be just n. So n minus 1 over n, again, you have your powers the same on your leading terms, that's going to equal 1 when you take the limit, which is greater than 0, which is finite. And this is going to also converge by the LCT. It's going to do the same thing as what your comparison series did. So again, here, probably would have used the exact same n to the 5/2. So you can see that 3/2 goes into 5/2. That would subtract and leave us 2 over 2, or just n to the 1st.